Today we are looking at lesson 7, trigonometric limits and the squeeze theorem. So we will use the squeeze theorem to evaluate trig limits. Now, on some of our previous practice problems, we kind of had a happy little accident in there in that you've already been exposed to this. You've already seen it. And some of you had some red flags that went up and said, hey, wait a minute, this isn't working. So let's jump into our warm-up. We want to evaluate the limit as x approaches 0 of sine of x over x. So again, just like any limit problem anywhere, the first thing you have to do is put in the 0. So I've got sine of 0 over 0. Sine of 0, again, that unit circle, you've heard me talk about it a lot the last few days. The sine of 0, as a reminder, if you're over here, here's 0. Your ordered pair is, I just did that backwards. Your ordered pair is 1, 0. So sine is the y value. So sine of 0 is 0 over 0. Well, we've seen that before. We should be able to go back and factor and simplify and use a conjugate pair. But I can't factor sine. And sine is as simple as it gets and nothing cancels. And I don't ever, ever, ever want to see this. You cannot cancel those x's. Don't ever, ever, ever do that. So there's nothing to simplify. So we need a different method. So we use something called the squeeze theorem to prove what the limit is, even though we can't calculate it directly. So the squeeze theorem says this. If it's indeterminate with no way to simplify, we squeeze it between two other functions. So if you look at this picture over here to the right with me, h of x is the function on the top, f of x is the function on the bottom, g of x goes in the middle. So there's kind of one piece of information that's missing off of this graph. You would say that f of x is less than or equal to g of x, which is less than or equal to h of x. So the f function is always below the g and the g is always below the h. Basically, they don't cross anywhere. So if we look at a particular point A, if we're looking right here, what we can do is we can say, all right, if function f has a particular limit, L, and function h has a particular limit, L, then function g has to have that same limit, L, because it's squeezed in between. And that's what those 3 dots right there mean, is therefore. So if the limit as, oh, I have a typo here. The limit as x approaches a of h of x is equal to the limit as x approaches a of f of x, and those are both equal to L, some number, then the limit as x approaches a, make this one an a, of g of x is also L. They have to be the same, so that's therefore. So we're going to evaluate the sine of x over x using the squeeze theorem. So here's the good news about this. We are going to prove it once, and then you are just going to use the result. So students always ask, how do I know which functions to use? The good news is you don't have to. Oh, excuse me. So we are going to use, let me look up above here. We said f of x was the function on the bottom. So I want you to use f of x is equal to cosine of x. And then I want you to use h of x is equal to 1. And we are going to use g of x is sine of x over x. I know what functions to use to prove the squeeze theorem here. You don't have to come up with those on your own. The AP exam is never, ever, ever going to ask you to do that. So on the right-hand side of my picture, I've got a graph, but I'm gonna hop over here to Desmos real quick and pop those in. So we are going to say that y is equal to 1. We are going to say that y is equal to, oops, come down here. Y is equal to functions sine of x, come out here, divide that whole thing by x, it did it correctly, so that's good news. And then the last one, I'm going to say that y is equal to cosine of x. Okay. Ta-da, all right, there we go. So we have this nice pretty graph and we're just focusing on this part in the middle. So I'm gonna zoom in, zoom, 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 zoom. Yeah, now now that looks good. So the red curve is 1, the green curve is sine of x over x, and that blue curve is cosine of x. And you can see that the 1 for this particular range, right around 0, 1 is always on the top, cosine is always on the bottom, and sine of x over x is squeezed through the middle. Now, you can stretch it and do crazy things. You can't see the open circle on that sine of x over x. If I had my regular TI calculator here, you'd be able to see that there's a gap in the table. If you looked at the table and zoomed in, it's undefined at 0, sine of x over x is. So we have our beautiful picture. We can come back here to our notes and jot something in similar. So here is cosine of x is already in there. This is cosine of x. This is 1. Mine went a little bit low. Equals f of x. We said cosine of x is, nope, I did that backwards. G of x is, or h of x is 1. All right, I'm going to zoom in over here too. All right, there's my curve of 1. And then sine of x over x, or maybe this was the sine of x over x graph. I think that was. So let's put the cosine graph in ourselves. Because when I look really, really close, it kind of looks like there's a pixel missing, but I don't know if that's from the 1. I'm not sure what that is. All right. Come back. There we go. Cosine of x equals, okay, we make some adjustments as we go here. And then this will be our sine of x. Okay, there they all are. You can see that they're squeezed together. So because the limit as x approaches 0 of cosine of x, so again, substitute that 0 for x, cosine of 0 is 1. And the limit as x approaches 0 of 1, well, that's a constant. And we talked about that rule earlier with our limit rules. The limit of a constant is always that constant. So this is 1. So because h of x is greater than g of x, which is greater than f of x, and they both have a limit of 1, my h and my f, we can say, therefore, the limit as x approaches 0 of sine of x over x must also be equal to 1. So that right there, my friends, is the good news. This is what we need to remember. You don't have to remember how we came up with it. You don't have to remember what functions we used. You just have to remember the end result. So let's look at example 1. We're going to jump right in here. What is the limit as x approaches 0 of sine of 1 over x? The limit as x approaches 0 of x, this is multiplication, sine of 1 over x. We're going to jump right in. Okay, so with multiplication, remember you can take the limit of each one individually. So the limit as x approaches 0 of 0, and this is, make this an x. And the next one is the limit as x approaches 0 of sine of 1 over x. So you can really turn them into 2 limit problems. So the first one's pretty good. The limit as x approaches 0 of x. Well, you substitute the 0 in for x, and there you get an x. All right, sorry for that little pause there. And then we have to evaluate the second piece, the limit as x approaches 0 of sine of 1 over x. Well, if I substitute that 0 for x, I've got 1 over 0. So let me come over here, sine of 1 over 0. This 1 over 0 piece, when we divide by 0, we know that that's infinity. It's either positive or negative infinity. So this is the sine of infinity. Well, think of your sine graph. Sine looks like this. Passes through the origin, looks like this. If I approach infinity, if I go, whoops, how did that happen? If I go to infinity all the way to the right, this keeps oscillating between positive and -1. It never comes to one value. Therefore, it doesn't exist. So this piece doesn't exist. So as soon as you have a part of your limit that doesn't exist, the whole solution does not exist. Now, I want to show you a graph of this. There we go, quick pause and like that, magic, we have the graph. So this is the sine of 1 over x, and we want to find the limit of this piece as x approaches 0. If you look at this graph, it gets kind of crazy in the middle. And when we're in class and I have students look at this at their TI 83s and 84s, I just have them keep zooming. Zoom, 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 zoom. On Desmos, I'm just going to pinch. But as you get closer, this is a mess. It just keeps oscillating up and down and up and down and up and down. And in fact, did I break it? Oh, look, now I can't go back. I can't zoom back. Oh, there we go. Now I can zoom back out. It's a hot mess. It's going up and down and up and down. There is no limit there. It doesn't exist. So we can come back to our notes and confirm that that other piece does not exist. So the limit here does not exist. Two other important trig limits that also come around from that squeeze theorem. I'm not going to prove them to you, but you can just kind of put them in your toolbox. The limit as theta approaches 0, 1 minus cosine theta over theta is equal to 0. That one's given to us. And this is the first one here that we already discussed. So limit of sine of theta over theta equals 1. We used x before, it's okay. 1 minus cosine theta over theta equals 0. The key is the angle within the trig function has to match the term in the denominator. And the reciprocal of those two statements also works. So when I say reciprocal, I mean you can flip them over and they're still true. For example 2, we want to find the following limits. The limit as theta approaches 0 of 4 theta over theta. So the key is we need that sine of theta over theta. That's what needs to match. In this problem, we have a 4 in the numerator with this theta, but you don't have a 4 in the denominator. So I'm going to tell you to put 1 in. But if you put a 4 in the denominator, you've just divided the whole function by 4, and that's not equal, that's not allowed. So you have to put 1 in the numerator as well. Now, what happens is this whole piece, the sine of 4 theta over 4 theta, becomes 1. So the limit as theta approaches 0 of 4, that piece on the outside, this whole piece becomes 1 by that sine of x over x piece as x approaches 0 equals 1 by that squeeze theorem result. So our answer is 4. Okay, takes a little getting used to. This one's a little bit weird. Letter B, tangent. The first thing we do with any limit problem, and I forgot to do it on the last one, is make sure you get 0 over 0. So this becomes tangent of 0 is 0 over 0. We got 0 over 0. So we need to do something else. We can factor, we can simplify, but those don't work. So simplify trig, the limit as x approaches 0, tangent is really sine of x over cosine x all over x. Now, I'm dividing by a fraction, so maybe you want to do sine of x over cosine of x. Instead of dividing by x, we multiply by 1 over x. This becomes the limit as x approaches 0 of sine of x, excuse me, x cosine of x. Excellent. Now inside of here, I see that sine of x over x. There it is. That piece becomes a 1. So this is the limit as x approaches 0 of 1 over cosine of x. Now our job is to substitute that 0 for x. So cosine of 0 is really 1. 1 over 1 is 1. Excellent. Sometimes you'll see some textbooks put that one up here with the important ones to know. It just depends. So the limit as x approaches 0 of tangent of x over x is also equal to 0. If you wanted to, you don't have to. All right, 2 more. That zoomed out really far. Okay. The limit as x approaches 0 of sine of 3x over sine of 5x. Students kind of always go a little crazy on this one. So if I put 0 in for x, I get 0 in the numerator, 0 in the denominator. It's indeterminate. I can't simplify the trig any further. It's not going to be any kind of factoring. So I want you to rewrite this, but space it out a little bit. So this is the sine of 3x. Give yourself some space, or the sine of 5x. Okay. I'm sorry if you can hear this is Maggie. Say hi, Maggie. She's very cranky this morning. Okay. So what we need is that sine of x over x piece, which we don't have. So we're going to divide the top by x and the bottom by x. I did it to both the numerator and denominator, so we're okay. In the numerator piece, you need to have a 3 to match with this 3 in the top. So I'm going to put a 3 with this x. Now I'm going to think of just this upper fraction and put a 3 here. I'm balanced again. When you look at the denominator, same idea. Oh, let's pick a new color. Let's pick purple. So the numerator of the denominator has a 5 in it, so I need a 5 here. I'm going to put a 5 here. Now, remember, you're on the lookout for sine of x over x. Sine of something over the same something is equal to 1. Sine of something over the same something is equal to 1. Excuse me. And I should clarify, that's only true when x approaches 0. If x approached pi over 2, this would not be true. If x approached 4 pi, no, we get a little bit bigger out there. You just have to make sure it says x approaches 0. So actually at 4 pi, it wouldn't be 0. It's only as x approaches 0. This becomes, let's rewrite all of this. The limit as x approaches 0 of 3 times 1 over 5 times 1. This is 3/5. Now, here's what I love to tell students. Mrs. Charnley, Mrs. Oakes, when I have that original problem, can I just cross off the signs? Can I just cross off the x's and be left with 3/5? No, there is no legal math anywhere that allows that to happen. Does the answer wind up to be the ratio of the coefficients? Yes, that's true. But I don't ever, 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 ever want to see you cross off the sign or cross off the x's. Don't do it. I'll send you back to pre-calc for a refresher. Don't do it. You do have to go through the other steps, but if you do enough of these, you start to recognize that there's a definite pattern there. And our last example here, example D, the limit as x approaches 0 of sine of, nope, that's not sine, tangent of 3x over 4x. So again, first thing we always do is put in that 0, tangent of 0 is 0, 4 times 0 is 0, so we've got 0 over 0, it's indeterminate. I would take that numerator and break it into sine of 3x over the cosine of 3x all over 4x. That sine of 3x over cosine of 3x is really the same thing as your tangent. At this point, I would rewrite it. This is kind of a complex fraction you've got going on. I would move that cosine of 3x to the denominator. So sine of 3x over 4x cosine of 3x. So the denominator of the numerator moves to the denominator. You could also do the multiply by the reciprocal over here if that's what you're used to. If that's what you see. When I look at this, I actually just multiply top and bottom by cosine of 3x. And then these cancel out. Anyway, that's what I see. We're still on the lookout for that sine of x over x, and I'm close, but I'm not there yet. So I've got the sine of 3x, sine of 3x. Here's the x. I need a 3 and I have a 4. So what I'm going to do is I'm going to rewrite this a little bit. Just kind of space it out. The limit as x approaches 0, I'm going to say the sine of 3x I'm going to put this x in the front just so I can organize my work. I'm going to move the 4 over here, cosine of 3x. So I haven't done any math in that step. I've just rearranged a little bit. Now, if I have that 3 in the numerator, I know I need the 3 in the denominator. So I'm going to put the 3 here and put this 3 out here to keep it balanced. Now, when I look at this, I have the sine of 3x over 3x. The sine of something over that same something. So we're good to go. So this piece is equal to 1. So this is the limit as x approaches 0, 3 times 1 over 4 cosine of 3x. And we still have to evaluate this when x equals 0. So the numerator is 3 times 1. The denominator is 4 times the cosine of 3 times 0. Well, 3 times 0 is just 0, so cosine 0. So my numerator is 3. Cosine of 0 is 1, so this is 3/4. And again, it is the ratio of the coefficients, but you cannot cancel out the x's. It doesn't work that way, but you do wind up with 3/4. So these are a little bit more challenging than some of the algebra problems. Sometimes there's just this little nuance or a little sign or a little fraction somewhere that can change the whole problem. So don't be afraid to reach out. I know with this hybrid schedule that you only see Mrs. Oakes in person 2 days a week. But I've been getting emails. That's great. You can email me. You can email Mrs. Oakes. You can see her in person. We're kind of sharing double duty here for you guys. So you get the luck of 2 teachers. But do ask questions. Please, 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 please ask questions when you get to those practice problems. So good luck and let me know how you do.